This is fundamental problem 3 from chapter 18. In this problem, the uniform 50 kilogram slender rod is at rest in the position shown when a force of 600 newtons is applied, here. Determine the angular velocity of the rod when the rod reaches its vertical position. Okay, so the rod is starting off like this. This distance is 4, this is 5. So this is a 3, 4, 5 triangle. This is initially. And finally, the rod is in its vertical position like this. And this would be 5 for the length of the rod. We're going to use work energy to solve this problem. And rather than using equation 1814, I'm going to use equation 1818. For the potential that I have here, since there are no springs in this problem, that would be gravitational potential energy. And I can say T1 plus V1, so initial kinetic energy plus initial gravitational potential energy, plus the sum of the work done by all other forces, which in this problem is just going to be the force P. So the work done by force P is equal to the final kinetic energy plus the final gravitational potential energy. But really, I don't need to find the initial gravitational potential energy and the final gravitational potential energy. All I need is the difference between the two, or I could just say V1 is equal to 0. I'm going to bring the V1 over to the other side and say kinetic energy plus work done by the force P is equal to final kinetic energy plus the change, and this is just gravitational potential energy since there's no elastic force in this problem. Okay, so I need to find what these four quantities are, then I can use my equation. So initially, the rod is at rest, so T1 is equal to 0. Next, let's look at the change in gravitational potential energy. So the rod starts off like this. The rod's 5 meters long. The center of mass is halfway along the rod. And now for our gravitational potential energy, we're looking at the mass center. And the mass center is at this height. If we use this here for our datum, in the vertical direction, we know this distance is 4, so that distance would be 2. And finally, when the rod is vertical, so our datum would be here, and so we're measuring from this line here. This is 2.5. Since the rod is now in its vertical position, the mass center is 2.5 meters away from this line here. So for the change in gravitational potential energy is m times g for the weight times y. So it's m times g times the change in y. We're ending at a higher height. The change in height is 0.5, so this is m times g times 0.5 meters. Now, for the work done, the force P is being applied here. The displacement is in the same direction as the force. So when we do the force dotted with the displacement, we just get the magnitude of the force times the magnitude of the displacement. The force is constant, so when you do the integral here, cosine of the angle is cosine of 0 degrees, so that can come outside. I mean, that's equal to 1. The force is constant, so the force can come outside. So for the work done by the force P, we have our constant force P, which comes outside. Then when we integrate ds, that just gives us the change in position. Well, we started here, and that was 3 meters away from where we end. So when the rod is vertical, now roller B is here. So where the force was applied at roller B, it was applied in this direction. Roller B was moving this way, and roller B moved a distance of 3 meters. So that's 3. It's positive because the displacement and the force are going in the same direction. And our force P is 600. So this is 600 times 3. That's 1,800. And finally, I need to find T2. Okay, now I have to use what I learned in chapter 18. So now we have translational kinetic energy and rotational kinetic energy. But if I know where the instantaneous center is, then I can use that, and instead of having to calculate this term and this term, I just have 1/2 times the moment of inertia times of the instantaneous center times omega squared. Well, when the rod was moving this way, the end of the rod here was going up, and if roller B kept going this way when the rod is vertical, then this point would be moving back down again. So roller A is only moving in the vertical direction, and it's at its highest point right here. So this is our instantaneous center. So for the kinetic energy at event 2, I can say 1/2 times the moment of inertia for the instantaneous center times omega squared. And then, since it's a slender rod, I can go to the back cover of the textbook and look for the moment of inertia for the slender rod, but it's rotating about one end because I'm looking at the instantaneous center, which is at the end of the rod. So that would be the x prime axis or the y prime axis, which is 1/3 ml squared, or you could use the parallel axis theorem if you remembered the moment of inertia about the x or the y axis. So this is 1/2 times the moment of inertia of 1/3 times the mass times the length of the rod squared. The length of the rod is 5, and then times omega squared. So now we should have everything that we need, and we can plug it into our equation here. And T1 is equal to 0. The work is equal to 1,800. T2 is equal to 1/2 times 1/3. That's 1/6. 5 squared is 25, so that's 25 divided by 6. The mass is 50, so that's times 50 for the mass times omega squared, plus the change in gravitational potential energy. M is 50, G is 9.81, and the change in height is 5. Okay, so now we were asked to find the angular velocity of the rod when it reaches its vertical position, so we can solve for the angular velocity, and you can do that on your own. You should get 2.73 radians per second. That concludes fundamental problem 3.